Hello, everyone. Good morning. Welcome to our 9 a.m. press conference, the first aircraft crash investigation on another world. I'm Samson Rainey from AGU Media Relations. We'll begin with the panelists giving brief presentations describing their work, and then we'll open it up to questions from registered reporters. We'll end at 9:45 or when there are no more questions. Slides and additional materials from the briefing will be posted to the Press Information Exchange on AGU Connect, and we'll drop a link to that in the chat. This event is also being recorded, and the recording will be posted to AGU's YouTube channel and linked to the Press Information Exchange. Please bear in mind, please bear with us if there are any technical issues. If you have any questions about that or any issues at all, please email news@agu.org. All right, so let's introduce our panelists today. We have Lindsay Hayes from NASA headquarters, Travis Brown from JPL, Hovard Grip from JPL, and Terry Zanetos from JPL as well. So let's begin. Thanks.
Thank you very much. Okay, again, my name is Lindsay Hayes. I'm the Senior Scientist for Mars Exploration at NASA headquarters. I'm really happy to be here today to talk with you all about the Ingenuity helicopter. Just as the Sojourner rover paved the way for our exploration of the Mars surface with larger, more elaborate, more complex rovers, Ingenuity was the latest in the history of technology demonstration spacecraft. In both its operations and towards the end, as we will learn today, it has taught us quite a bit about flying on another planet. And so to tell us more about its operations, I will pass this on to Travis.
Oh, great. Thanks, Lindsay. So yes, I'm Travis Brown. I'm the Chief Engineer and Team Lead for Ingenuity. And today I'm going to, it's my great privilege and pleasure to present the first aircraft accident investigation on another planet. So let's jump into it. This investigation was undertaken by JPL and our partners at AeroVironment, who contributed major components to the mechanical system on Ingenuity. And so without further ado, let's start with a little recap. Ingenuity and Perseverance landed on the surface of Mars roughly 4 years ago. About 2 months after that, Ingenuity took her maiden flight, and in doing so became the first aircraft ever to fly on another planet. Excuse me. We like to make comparisons with the Wright Brothers airplane, that 1903 Wright Flyer, and that's because they are both technology demonstrators. It's purpose-built craft specifically to prove a point, and that is, can we fly, in our case, on Mars, right? And as it turns out, and you're going to learn in a minute, they actually met a similar end to their career. In both cases, they were in a test flight. They had a hard landing, which rendered them unflyable, but largely mechanically intact. So that's a little spoiler. So that the people here are gathered because we're all enthusiastic and excited about aircraft. We believe that though Ingenuity was the first aircraft on another planet, it shouldn't be the last. And so as a result, we did this investigation to try to learn everything we could from that crash. We're looking at things that we can learn from how she broke, where the failure points were, and even though Ingenuity was a phenomenal success, obviously far exceeding all of our expectations, it's still useful to look at how it ultimately broke when we pushed that envelope. Okay. So here's her first flight. Oops, sorry. So just a quick video, you can start. So just a quick recap of the mission to set the stage and the context for this investigation. So Ingenuity had a 5-flight, 30-sol tech demonstration phase. After that, having done all of the objectives that we set out to do, NASA extended the mission to an operational demo phase where we pushed her further, higher, faster than anything we had ever planned to do prior. We traveled into terrain that was far rockier, more rugged, more sloped, had fewer features. We performed numerous tasks that we hadn't planned to do. So things like operational scouting for the Perseverance rover, science scouting, reconnaissance of things like the EDL backshell, things that had never been seen before and never done before. And then we even went through the Mars winter, which was a particularly taxing time. There's very little sun. The thermal envelope changes a little bit. And so we even survived that. So we went through all of these things over roughly 3 years of Mars flight. Now, by the end of 2023, we were approaching this region here. This was essentially this was coming up on the beginning of the Mars dust storm season. And we had just completed a successful engineering test campaign with flights 68 and 69, shown here. And at that point, the determination had been made to rendezvous with the rover for a close-up engineering inspection at Bright Angel. This was likely to be the last thing we did before the storm season started. And the path to Bright Angel is shown here. It's a sandy region full of sand ripples, kind of surrounded on both sides by rocks and very unpleasant terrain, things that present a significant landing hazard to Ingenuity. Now, historically, throughout the mission, sand ripple fields like this had been our bread and butter. We landed and flew over regions like this all the time. And so that's the path that was plotted. And that started relatively uneventfully with Flight 70. So here's a picture from Flight 70 looking toward Bright Angel. Now, there was some indication that potentially the vision system on Ingenuity was starting to struggle, but it was very much within the realm of what we had seen in past flights. So it was totally expected. By Flight 71, however, that vision navigation trouble eventually triggered an emergency landing. And because of the way that emergency landing occurred, we didn't have a good idea of specifically where it had landed, and more importantly, the heading that it had, so which direction it was pointed. And that gave us essentially two choices to come out of that 71 emergency landing. One was we could fly blind, that is, fly a path without full knowledge of where we were pointed. The risk being that we could run into these rocks on the side. And the other option was what we more typically do, which would be to pop up, take some pictures of the terrain, and register those against satellite imagery. So that's what we did. So 72 was that pop-up flight. And as you guys know, that was our last flight. And with that, I'm going to turn it over to Howard Grip, Ingenuity's original GNC, Guidance, Navigation, and Control development lead, and chief pilot for the first half of the mission, for all the details.
All right, thank you. In investigating this flight, one thing that's becomes clear is that it's really a tale of two flights. Flight 71, in which we had an emergency landing with a hard touchdown at high velocities, and Flight 72, where we lost contact with the aircraft right before touchdown due to a power outage, and then ended up on the ground with a damaged rotor. These two flights, they are similar in terms of the symptoms that we see during the flight, and the way that Flight 72 was planned and operated is a direct function of trying to recover from what happened in Flight 71. One of the things that makes it difficult to investigate this is the relative lack of information. The accident site itself is about, it's more than 100 million miles away. There's no black box, there are no eyewitnesses. We can't walk up and touch anything. So we have to work with the, small pieces of information that we have. So these are some of those, pieces of information. We have planning artifacts that describe the decision-making process taken prior to the flight. We have limited telemetry. The aircraft told us its estimated position, velocity, and attitude during the flights, which cuts off shortly before the end of Flight 72. Then we have something called event logs. These are messages that the helicopter sent out during flight. And finally, we have images from the helicopter taken after the flight, as well as by the Perseverance rover from a standoff distance of about a few hundred meters. So what we tried to do is take this information and try to tease apart exactly why did this happen and how did it happen. And to start with the first part, excuse me, why it happened. The root cause of this was degraded navigation due to visually bland terrain, possibly in combination with high local slopes. The way this helicopter works when it navigates is by looking down on the ground with a camera, and I'll show you an example of that in the video playing here, is it looks down on the ground with the camera and tracks distinctive features on the ground that are moving across the field of view. And that is how it can estimate how it's moving relative to the ground. For this to work, obviously there has to be things to look at on the ground. There has to be enough feature richness. And in the area that we found ourselves in Flight 71 and 72, there simply weren't enough things to look at. And the reason we can say that very confidently is that the helicopter told us about it itself. So if you look on the right side here, you see these event logs from Flight 71 and 72, and you can see that the helicopter is saying very loudly, I don't have enough things to look at. There aren't enough features to track here. And in Flight 71, that resulted in an emergency landing. And in Flight 72, we see that same pattern repeating itself. And the fact that we touched down with high velocities is exactly the kind of thing that you expect to happen if you have degraded navigation, because one of the main functions of the navigation system is to keep track of the helicopter's velocity. In Flight 71, we have enough telemetry that we can tell with certainty that the helicopter touched down with a horizontal velocity of about 2.5 meters per second. That's about 5 times what the helicopter was designed to take. But we survived Flight 71. But we can also see from Flight 71, we have images taken by the helicopter that shows telltale signs on the surface of what happened during that touchdown. So we can see signs that the helicopter bounced and plowed through the surface, and we can see sand spray going from the landing gear out in the direction that the helicopter came from. Now in Flight 72, we don't have as much telemetry, but we can see the same kinds of signs on the surface. Again, we see signs that the helicopter bounced, plowed through the sand, and threw sand away from the landing gear. And so from that, we can infer that in Flight 72 as well, we had a hard landing with high lateral velocities. Immediately after the accident, our main theory was that one or more of the blades had touched the ground, contacted the ground, and that is how the blade got damaged. It seemed logical at the time, but one of the main things to come out of this investigation is we're actually reaching the opposite conclusion. We do not think that the blades contacted the ground. Instead, the blades were damaged due to loads, bending loads, originating from the root of the blade, where it's attached to the mast of the helicopter. One reason we believe that that is the case is whereas we can see very clear signs on the surface of where the landing gear touched the surface, we do not see any signs on the surface that are consistent with the blades contacting it. And another thing that is maybe even more compelling is that we now know that this is not just 1 or 2 blades that are damaged. As far as we can tell from the images, all 4 blades are damaged in much the same way, with the tips snapping off about 1/3 of the way from the tip, which suggests that they all were subjected to similar loads and that they broke at a weak structural point along the blade. In addition to that, it's worth noting that one of the blades actually came loose in addition and then was flung out about 15 meters to the side, which you can see here. So we actually went, as part of this investigation, we went and did a structural analysis to identify, well, let's suppose that it was indeed subjected to bending loads at the root. Where would it be likely to break? Where is the structural weak point here? And what we found is that the highest stress concentration where the blades would be most likely to break is about 60% out from, of the distance from the root to the tip. And that is very consistent with the visual evidence that we have from Mars. That is just about where the blades did in fact break, which lends a lot of strength to this conclusion. This does not mean that we've been able to figure out everything about the flight. Our conclusion is that we don't have enough information to disentangle some of the details about the sequence of events right around landing. That is about the last second of flight. We think it's most likely that the rotor was damaged when the landing gear touched the ground because of the loads generated during that event. But we cannot rule out that because of fatigue over time and possibly even damage, unobserved damage from the previous flight, that the rotor was weakened to the point where it could have, with an aggressive maneuver right before landing, that it could have broken up directly before landing. We also think it's most likely that the power outage that we saw happened directly after landing in conjunction with the rotor breaking up. But we cannot rule out that the power spike happened a little bit before we touched down as well. We simply do not have enough information to make confident distinctions here. But I'll elaborate a little bit on what we think is the most likely hypothesis, which is illustrated in this diagram. In this case, we came down similar to Flight 71, with high velocities, high lateral velocities, and had a hard touchdown. And what happens in this case is the helicopter, because of the force on the landing gear, will tend to want to align itself with the surface very quickly. It will sort of whip around. And with the stiff rotor on Ingenuity, the rotor itself, it has to follow that motion as well. The tips of the rotor blades, they're traveling at about 400 miles per hour at this point. And that velocity has to change direction very abruptly. And just as if you can picture, a race car going that speed around a corner, you'd see some very large forces. You would feel that. And those forces were felt by the rotor blades in this case. And what can happen in that case is that the tips simply snap off. And that's consistent with what we see on the surface. We have a few recommendations that we're making as a result of this investigation. The first one goes directly to the root cause. A future helicopter for navigating across general Martian terrain needs greater navigation robustness to terrain, specifically feature richness and high slopes. We also believe that future helicopters have had more robust log handling, specifically be able to preserve logs in case of anomalies, which Ingenuity was not able to do after the emergency landing and after Flight 72, which made investigating this quite difficult. Finally, we had this power outage as a result of a power spike that shut down the avionics. And we believe future helicopters should be made to more gracefully degrade by prioritizing power to the avionics in a case of a power spike. So wrapping up the big picture, part of what we did here is we also looked at, were there any mistakes made in operating a helicopter? Were there any regrets? Are there things that, with the benefit of hindsight, that we should have done differently? And the answer is no. What happened here is any piece of hardware, if you push it far enough beyond its design limits, sooner or later it's going to break. And this team had a mandate to keep pushing this technology further and further to achieve more and more. And it was successful in that for 3 years. And after 3 years, in Flight 71 and Flight 72, what happened is we simply found out exactly where Ingenuity's limits were. And with that, I'll hand things over to Teddy.
Morning, everybody. So, what comes next? In addition to having the privilege of working on Ingenuity with Travis and Havard and our team, and when I say our team, I do want to mention it's NASA's Jet Propulsion Laboratory, NASA's Ames Research Center, as well as our partners at AeroVironment. We've been working on that answer for a handful of years now. Even before Ingenuity ever flew, we've been trying to figure out what might the future hold for flight on Mars. Before we get to that phase where we talk about our future concepts, I do want to mention on a lighter note that our baby's still alive. Ingenuity, aside from the rotor system, is still alive and well. If you were to query Ingenuity's health system, she's green across the board as far as she's concerned. She doesn't have a sensor on the rotor system to detect the damage. But we are very proud to report that even after the hard landing in Flight 72, avionics, battery, sensors have all been functional. And she still has one final gift for us, which is that she's now going to continue on as a weather station of sorts, recording telemetry, taking images every single sol and storing them on board. I think we have about 20 years worth of storage. Is that right, Travis?
That's about right.
Right around 20 years worth of flash storage on board. And eventually, when human astronauts get to Mars or an additional rover or additional aircraft gets there, we may be able to download those images, make a wonderful data set for scientists to go through one day. So thanks again, Ingenuity. What comes next, right? Just as the Wright Brothers had their first aircraft, the Wright Flyer, that led to propeller planes, jet aircraft, and of course, the airplanes that most of us flew in on this week to get to AGU. We believe the same thing will be happening at Mars. There will be a next generation, there will be many, and there will one day be fleets of aircraft flying around Mars. Starting in 2018, a good 3 years before Ingenuity ever flew on Mars, our collective team started working on that problem of how might we scale up, how might we try and tackle challenges bigger than a technology demonstrator might be able to do, and bigger than this 1.2 meter life-size model here to my left. This is what we came up with in 2018, which we first started calling Mars Science Helicopter. The main theme here is to scale up, to be more capable, to carry meaningful payloads for science, for example. Whereas Ingenuity was 1.8 kilos total, we're imagining concepts here for rotorcraft that can be in the 30 to 40 kilogram range, carrying science payloads or generic payloads in the 3 to 5 kilogram regime. Right, that's huge. Just to put things into comparison here with what our baby did here with Ingenuity, it's a significant scaling up of aircraft, but also in terms of actual science capability or mission capability. This now becomes our mission. Back in 2018, we didn't have the benefit of flying on Mars. We didn't have the benefit of all the experience that 72 flights in 3 years has now provided us. And in the course of the last 9 months, almost 12 months, the teams at JPL, Ames, and AeroVironment have been working hard to update this concept to the latest version, now with the benefit of all of those lessons learned. So for the first time, we're going to be showing you all what the latest generation of aircraft for Mars is going to look like. And we call her Chopper, all right? A few things to call out. Obviously, we're no longer a coaxial helicopter. We're sticking with the multi-copter theme. But a few things to point out. One, 6 blades on each rotor. That's a lot of surface to be generating lift. Solar panels on all 6 arms. There's a lot of good engineering reasons, and we'd be happy to answer any questions you have during the Q&A session. But it's a much larger platform, exploration platform, that we've designed originally for 3 forks, but it's a generic aircraft that can go all over the planet. Thinking about Jezero, not just Jezero Crater, but also Valles Marineris, for example, where this aircraft would be able to carry around, and here are the key metrics, 5 kilograms of payload and 3 kilometers per sol. Right? At 3 kilometers per sol, for example, you could cover the entire distance that Perseverance has driven in about 3 sols thereabouts. Call it a week. Throw some margin in there. In about a week, you could cover the entire distance that Perseverance has driven. So it's really a game changer when it comes to exploration and discovery. Here we have a short animation showing you all what we hope to be the future. One day having not just one, but hopefully fleets of aircraft flying around Mars. Here, for example, in Valles Marineris, where there is a lot of scientific interest to go explore. Just like the Grand Canyon is interesting here at Earth, we think, and scientists believe that Valles Marineris is extremely interesting for scientific reasons. And we hope that this platform will one day be useful for all different sorts of scientific exploration concepts. And we can't wait to build it all. So with that, thank you all very much for your time, and that's all we had prepared for today.
Thanks, panel, for sharing your work with us. Very cool stuff. We'll now open it up to questions from registered press. Please state your full name and affiliation. If you're online, please use the Q&A box instead of the chat box, and you can either be invited to unmute or you can just type your question in and we will ask it for you. So starting with anyone in the room.
Hi, Jeff Faust of Space News. You mentioned, it looked like in one of those pictures that you've gotten images, at least in the last few months, from Ingenuity. I think the last contact you had there was like in November. Just sort of what, when will be the last contact you have before presumably Perseverance is too far away to actually get any more telemetry from it?
So we're actually nearing that point now. We're currently a little over 3 kilometers from Perseverance. or rather Perseverance has moved more than 3 kilometers from us. That's actually farther than we ever thought we could get radio comm. So we already expected to drop out at this point. That said, Perseverance is about to scale a large terrain feature, at which point it will go over that terrain feature and we'll lose line of sight. And so I think it's a good bet that within the next month, we'll lose contact forever, or until we come back in 20 years with astronauts.
Until we return.
Or until we turn back
Sample for sample return.
for sample return, yeah.
Becca has an online question.
We have a couple of online questions here. Leo Enright from Irish TV asks for Lindsay, what is the current status of the rapid mission design studies for MSR?
Those studies have been, the reports have been turned in, and they are currently under review, and we are currently on schedule with that whole rapid mission design study process.
And we have one from Joel Achenbach at the Washington Post. Can you explain again why the helicopter had a navigation issue? Was it featureless terrain? Thank you.
Yeah, so this was a vulnerability, if you want, or I wouldn't call it a vulnerability. It's a part of, this kind of system is it relies on visual features. And we knew when we traveled to Mars that we had to pay attention to this. So when we first selected a site to put down Ingenuity, we selected one that had lots of features. If you look at pictures from Wright Brothers field, you'll see that there's lots of visible bedrocks, little pebbles and stuff, lots of things for it to lock onto. So we felt, we were playing it safe with that at that point, and that was specifically a concern that we had. So we played it safe for the tech demo. And then as we kept going after that, we gradually kept pushing it and we flew across more challenging terrain. And the helicopter kept performing, even flying over, very sandy terrain. What happened here in flight 71 and 72 is we flew into an area that was even more bland than anything that we'd seen. And we can see it even in flight 70, where we first entered that area, that it is having quite a challenge tracking the features. And then of course in flight 71 and 72, it has to effectively give up on that. So this was a known thing, something that we were very careful with up front, and that receded more as a concern over time. And then, it came back in his last 2 flights and turned out to be the particular limit that we hit that would end the mission.
And if I could also add to that, like Havard said, it was well known that capability limitation with Ingenuity. The amount of mass invested in Ingenuity and its cameras, fractions of a gram, thereabouts, call it a gram. It's well understood what we would do for future rotorcraft to improve that capability. You could have more than 1 gram invested for your camera and have a much better resolution on your featureless terrain. And B, if you have a targeted mission going somewhere, you have a better idea of what that terrain might look like, so you can plan for that in advance. In no universe did we imagine 3 years ago when we started Ingenuity's tech demo mission in a comparable parking lot, if you will, of ideal terrain selection, that we would be flying in such a featureless terrain, right? But just want to drive home the point. We know exactly what to do for the next generation to be able to handle those challenges and perform even better.
Thank you. Christina Reed with the National Institute of Standards and Technology. And I'm just curious, what's the reasoning behind the word choice of calling it a helicopter or a rotorcraft as opposed to a drone?
A handful of considerations went into it. The main one is it's technically appropriate to call it a helicopter. It is a helicopter. Drone has a lot of different connotations. People think quadcopter a lot of the times when you buy a toy in the mall, for example, or other more industrialized applications for drones. Helicopter is, especially because it's a coaxial, is very appropriate.
Oh, we have a question online, Becca?
Yeah, we have a question from John Amos. Are there any lessons here for the Dragonfly mission to Titan?
So I guess I'll talk about ops if you want to talk about any other. Yeah, there's a handful of different lessons learned, and we're writing up a bunch in a report. We've already published a lot of different blog posts about some of our lessons learned as far as Ingenuity is concerned. And one key area that we think we can contribute to future missions like Dragonfly is trying to hand off those operations lessons learned. How do you plan a sortie? How do you deal with your tactical timeline? How do you deal with limited information like the team has done here in terms of our investigation? We think some of those lessons learned will transfer, others not so much. Let's remember here, Dragonfly is an RTG-powered, a truck in comparison to the small Leaf that Ingenuity is flying around the skies on Mars. So it's a much bigger aircraft, different power constraints, different thermal constraints. So operations, we think, will be one area.
Yeah, so Dragonfly is its own mission with its own challenges, and so we don't want to presume that everything that applies to Ingenuity applies to Dragonfly, but we want to at the same time share as much as we can about what we learn, so that they can have the benefit of what we learn. And some of those things I think are applicable. And then we're also participating in the context of, for example, reviews for Dragonfly, so we can share, use the benefit of our experience to give feedback in that context.
Hi there, I'm Kimberly Cartier with EOS. Going back to the navigation issue, you mentioned a couple different ways that you recognize that you might do better in the next generation. What, if any, of those solutions are under consideration for Chopper? And relatedly, what's the timeline for Chopper?
So first of all, Chopper is a concept with no specific timeline for a flight implementation. So it's a concept that is intended to put out there, a possibility for something that could be, and obviously we hope would be implementable in the future. Now we are taking the lessons that we're learning from Ingenuity into consideration in Chopper, and that includes looking at different cameras, which Teddy hinted at. It also includes looking at more sophisticated fault protection. One of the things, and again, this goes back to what Ingenuity was. It was intended to do, a little hop in a very confined area. There wasn't a need for a lot of sophistication here. But one simple measure here would be for it to have the intelligence, so to speak, to just back out of an area when it can tell itself that it's not navigable. It was able to tell that in this flight, and if it had the right kind of fault protection, you could envision it just going back where it came from. So there are some relatively simple things like that that we can implement to add a lot of robustness to future designs.
Another question online?
Yeah, we have another question from Joel at the Washington Post. He wanted to hear a little bit more about what kind of damage occurred during the Flight 71 hard landing that influenced what happened on Flight 72.
So we're not aware of any damage. We did some pretty extensive health checks right after Flight 71 that did not suggest that we had sustained any damage. So we gave it a clean bill of health after that flight. That being said, it's possible that there could have been, kinds of damage that just wasn't observable in these kinds of tests. So as I mentioned before, there's some uncertainty about, what was the state of the rotor and how susceptible was it to being damaged at this stage of life, having flown on Mars for 3 years, and after having had an event like Flight 71 behind it. And that's one of the uncertainties that simply, it's more or less unknowable for us, and so yeah, it could have factored in. But we have no specific reason to think that it did, and so it's yeah, that's mostly just a possibility with no proof.
I think this might be a good time to add, Ingenuity as a tech demo did not have all the bells and whistles. You could imagine, a larger, lower risk mission would incorporate additional sensing to do better health checks. If you look at commercial airlines, they have a variety of sensors to be able to diagnose issues. The blades are particularly difficult though, right? So In that case, there really was no good way to check it. Yeah, we have actually a blade here that Hovart's holding up.
I was supposed to show this while I was talking before, and I forgot.
And it was right in front of you.
I know, I can't believe it. But yeah, this is an example. This is, a test blade from our campaign here on Earth, but it's identical to what flew on Ingenuity. It's just to give you a sense of what it looks like. Very light, very stiff, and right around here is where the blades broke on Mars.
I'll also actually just add one note, which is that, today, in fact, the Mars Exploration Program is rolling out its future plan. And part of the future plan is thinking about, sort of targeted Mars technology development and thinking about, what are the things that we can improve capabilities for science-enabling missions going forward. So while this concept isn't, specifically written into that plan, we're certainly thinking within the Mars Exploration Program about what the next 20+ years will look like of Mars science exploration. So if you're interested, that event is also happening later today, or in fact tonight.
Oh, one more question in the room.
Carter Emard with the American Museum of Natural History and Open Space Software. We were looking at plotting a visualization of this, and I was just wondering, is the flight data available beyond just the information in the headers of the images? Thank you.
Yes, I'll take that. So as the mission is winding down, we are in the process of closing out. And one of those things is actually making that data publicly available. So the current intent is to publish the entire set of engineering data that includes housekeeping data as well as high-rate telemetry from the flights in the planetary data system, so PDS. That should be coming in, in the next several months.
Okay, because my high school student of Burmese descent is actually doing this work, and so I have till May with her. She's very smart. She's headed to Caltech, but anyway, would it be possible to obtain that flight data possibly in the time span? Thank you.
Yeah, I think that's completely doable.
Another question online?
Yeah, we have 2 questions online. First, we have another one from Leo Enright, again of Irish TV. He has another rapid mission design studies question. Since these studies will presumably affect plans for MSR helicopters, the release was on February 14th, 2024, with a selection date of June 7th, 2024. Has there been some sort of delay in the selection?
So the selection for those rapid architecture studies did in fact happen. Excuse me. That information is all available publicly on the NASA ROSES site. There's information there about which studies were chosen. Those studies were submitted on time per the schedule that was also announced as part of that review. And like I said, they're currently in review with a specific review team. The information about that MSR studies review team is also available. We had a press release about it, so you can see that publicly as well. And we're currently sticking to the schedule that we had, which is they are being reviewed internally, and we're hoping for early next year that sort of a more broad picking a new plan or an architecture for MSR.
Thank you, and we have another online question, another one from John Amos. How far from its base station or its partner rover would Chopper be able to work? It would have better communications, presumably?
For all incarnations of Chopper or even any other future coaxial version of a helicopter that you could imagine, we envision having direct orbit capability. So while Ingenuity, again, as a tech demo, we had that radio leash back to our base station on the rover. Future aircraft, we've already designed a small radio that's about 150 grams that would be able to communicate directly to orbiting satellites. So there is no leash anymore. We can go anywhere on the planet that has satellite coverage.
Here we go.
Hi there, Jen Schmidt at EOS Magazine. I'm curious, can you talk a little bit more about Ingenuity's second act? Like, what can it actually measure, and I know you said that you're going to lose contact with it at some point soon, but what can we reasonably expect to learn with this 20 years of data that you can collect?
Yeah, so it's actually interesting. We've already learned some things from looking at that data, but I'll answer your question first. Ingenuity wakes up every morning. It measures its solar array current. It measures the battery temperature at wake up, measures the currents that it's drawing to keep its heaters warm. It measures, it actually enables its flight controllers, the FCs, to make sure they're still alive and well. It powers on its IMU. So there are a number of COTS electronics and avionics on Ingenuity that were honestly not expected to last even this long. So it'll be interesting to see how long they can last in that constant radiation environment on Mars. But also the solar and temperature trending that you can extract from it is very interesting. And what we've seen, this is what I was referring to, we landed on 72 shortly before the onset of the Martian dust season. So this was maybe mid-fall on Mars, and usually there's an uptick in dust. And what we saw in the several months that followed 72 is we actually saw significant solar panel array accumulation from dust. And then we've now gone through the winter where there's a second spike of dust. And so we've seen yet more accumulation. So what that tells us now is, we can start to model how much accumulation you get on an array in this area. It tells us, things about the atmospherics. And then the other thing is we're taking pictures every day. So we actually have the RTE camera pointed down, that's the 4K color camera, pointed down at the surface. And we did a shorter version of this experiment during conjunction where we essentially did a time lapse over 14 days. And you can actually see sand grains move. So we happen to be parked right now in a place that's active from an alien transport perspective. And so you can watch those sand grains move over the surface. And so think about what that would be over 20 years. You can specifically pick out sand grains as they go across. So, the scientists, I've talked to a lot of people who are really excited about that.
Absolutely.
It's not, necessarily the case that we'll ever get that data back, but it's there for the taking if we ever do want it. Yeah, we've seen a lot of motion even just in a few months, so see what the timeline looks like. We may not be able to find her.
Well, scientifically, that can be very important for understanding things like, climate and weather and things like that. It also has implications for understanding things that may affect human explorers and such. So there's a lot of information that you can derive from that.
Yeah.
And I will also add, on the engineering side of all of the metrics that Travis mentioned, we're extremely interested in trying to extract that data, right? Looking at my nerdy interests, for example, lie on the power side, right? I'd love to know exactly what might the cell spread be on those 6-cell batteries over 20 years. Now, we're probably not going to, we know that we're going to use better batteries for Chopper, for example, in its current incarnation, but still having 20 years of thermal degradation on the surface of Mars with commercial off-the-shelf lithium-ion batteries, that's hugely important to try and reason about what could you do next, right? If you had to take risks in location A or B or C. So there's a lot of great engineering treasure trove data in there, and I hope we do get that data set one day.
I think we have time for one more question if there are any in the room or online.
Just a quick follow-up to that. Any concerns about dust deposition on the solar panels that might reduce the power, sort of like what we saw with InSight?
Yeah, it's entirely possible. In fact, at this point, unless we get a dust devil or something to come clean the panel off, we probably wouldn't be flying anywhere near full capacity, if at all, at this level of degradation. Now, during the mission, we made a concerted effort to try to find ways to clean the panel off, and we had some potential success there, although the data is not 100% clear. It just happens that the place that we're parked is not great for that kind of saltation-based panel cleaning.
I just wanted to say one more time, again, I wanted to, reemphasize the concept that there is going to be the Mars Exploration Future Plan rollout this afternoon or this evening tonight. And I did want to just reemphasize this is a concept, and this concept specifically is not, we don't have any concepts in that Mars Exploration Future Plan. This is one concept that the JPL team has been working on, but the future plan is much broader and much more open. Thank you.
Thank you for that. This concludes our press conference. Thank you, everyone, for joining. Please join us for our next media availability, which is at 10 a.m. It is NASA and IBM using AI to make science more accessible. And back in this press conference room at 11 a.m., we have a retrospective look at the 2004 Indonesia tsunami and what we learned from it. Thanks.